Right now, more water than every ocean on the surface may be locked inside a single mineral buried 400 miles beneath your feet. Water that isn't liquid, isn't ice, isn't even a puddle, but atoms of hydrogen and oxygen trapped inside rock that has never seen the sky. And here is the part that doesn't add up. Earth condensed out of a ring of dust and gas so close to the young sun that water could not have survived there. Not as liquid, not as ice. It should have boiled off into space before a single drop ever settled. So the planet we live on formed dry, bone dry. And yet 2/3 of its surface is underwater, and there may be several oceans more hidden below. Where did all of it come from? If a question like that is the reason you keep watching this channel, do the thing that keeps it alive. Subscribe, hit like, and tell me in the comments what city you're in and what time it is where you are right now. I read them. Let me start with the problem, because the problem is stranger than the answer. When the sun ignited, it did what every young star does. It got hot, and it started pushing heat and radiation outward. That heat drew a line through the disk of debris swirling around it. Astronomers call it the snow line or the frost line, and it's exactly what it sounds like. Inside that line, close to the sun, it was too warm for water to freeze. Anything volatile, water, methane, ammonia, stayed as vapor and got blown outward or cooked away. Outside that line, far from the sun, it was cold enough for water to lock up as solid ice and stay put. Now here's where Earth sits. Earth formed well inside the snow line, deep in the warm zone, right where water couldn't hang around. The rock that built our planet came together in a place where any water molecule was a fugitive, driven off by starlight the moment it appeared. Mars is a little farther out. The asteroid belt is farther still. And it's out past the belt, out toward Jupiter and beyond, where the ice could survive. So the building blocks of Earth were, by every reasonable estimate, dry, roasted. And this isn't a fringe idea. It comes straight from where the frost lines sat in the early solar system, somewhere out between Mars and Jupiter, which means everything that assembled sunward of it started with almost no water at all. Picture the young Earth on the day it finished forming. A ball of molten and half-molten rock, glowing, pounded by leftover debris, sitting in the driest neighborhood you could pick. There is no ocean. There is no cloud. There is no reason for there to ever be one. And then, somehow, there is. That's the whole mystery in one sentence. The oceans have no obvious source. The planet was built in the wrong place to have them. Before we go hunting for where the water came from, we need to know how much of it there actually is. And the honest answer is nobody is completely sure, which by itself tells you something. You'd think this would be easy. Measure the oceans. Done. The oceans hold an enormous volume of water, and if you spread all of it evenly over a smooth Earth, it would cover the whole globe a couple of miles deep. That feels like a lot. And in human terms, it is everything. Every sea, every river, every glacier, every drop of rain that ever fell. But compared to the planet, it's a film, a varnish. If you shrank Earth to the size of an apple, the oceans would be thinner than the skin. All that water is barely a rounding error on the mass of the rock beneath it. Now here's the number that breaks the intuition. The rock beneath it may be holding more water than the oceans do. Not liquid water sloshing in caverns. The crust doesn't work like that. I mean water chemically bound into the crystal structure of minerals in the mantle. Hydrogen and oxygen stitched into the rock itself. There's a mineral called ringwoodite that lives in the transition zone of the mantle, a layer starting around 400 miles down. In a laboratory, it can hold a surprising fraction of its own weight as water inside its structure. And in 2014, a tiny flaw inside a diamond that had been coughed up from that depth was examined, and the ringwoodite trapped inside it turned out to be partly water. A direct sample, not a model, not a guess. A piece of the deep mantle brought to the surface by accident, dripping in the chemical sense. Run the arithmetic on how much water that whole layer could hold, and the estimates land somewhere between 1 and several oceans worth, sealed inside rock we will never drill down to reach. Read that slowly. The biggest body of water on Earth might not be the Pacific. It might be the rock. So the question gets worse, not better. It isn't just where did the oceans come from, it's where did all of it come from? The surface water and the far larger reservoir underneath, on a planet that formed in a zone that should have had none. For most of the last century, there was a comfortable answer, and it's the first place anyone looks, so let's start there. The idea was that the water sweated out of the Earth itself. Even in the dry zone, the theory went, the rocks that built the planet weren't perfectly dry. They carried a trace of water, a few molecules bound into their minerals. As the young Earth heated up, from the energy of all those impacts, from the crush of its own gravity, from radioactive decay in its core, that trapped water baked out of the rock. It rose. Volcanoes vented it as steam, along with carbon dioxide and other gases. The steam climbed, the planet cooled, the steam condensed, and it rained. It rained for a very long time. And the rain filled the basins and became the sea. This is called outgassing or degassing, and it's genuinely part of the story. Volcanoes do vent water vapor today. You can stand near an eruption and watch it. The early Earth had far more volcanic activity than now, and it certainly wrung some water out of its own interior over hundreds of millions of years. The trouble is arithmetic again. To fill the oceans this way, the rock that formed Earth needed to start with enough water to sweat out. And remember where that rock came from. The dry zone. The estimates for how much water those original building blocks carried keep coming up short. Not by a little, by a lot. You can bake the whole planet, and you don't get an ocean out of the inventory you started with. The reservoir wasn't there to begin with. So outgassing moves water around. It doesn't create it. It can't explain the total. Something had to deliver water to Earth from somewhere it actually existed. From outside the dry zone, from the cold country past the frost line where ice could survive. And that leads straight to the second great idea, the one that felt so right for so long that it became the textbook answer. Comets. Think about what a comet is. It's a chunk of the outer solar system, born far past the frost line, in the deep cold where water froze and stayed frozen. A comet is, more than anything else, a ball of ice and dust, a dirty snowball, in the old phrase, that spends most of its existence in the frozen dark and only grows a tail when it swings close enough to the sun for its ice to boil into space. Now line up the pieces. Earth formed dry. The early solar system was a shooting gallery, with debris crossing everywhere and impacts constant. And out past Jupiter sat a huge population of icy bodies, any of which could be nudged onto a path that crossed Earth's orbit. Send enough of them inward over a few 100 million years, let them slam into the young planet, and each one delivers its cargo of ice. Enough hits, and you've got your oceans. Water made somewhere it could exist, then carried to a place where it couldn't form on its own. It's clean. It's mechanical. It solves the frost line problem in a single stroke. You don't need Earth to make its own water. You just need the sky to keep dropping it in. For decades, this was the leading explanation, and it's easy to see why. It fits everything you can see with your eyes. The comets are right there. The ice is right there. The impacts obviously happened. What more do you want? Here's what you want. You want proof that the water in the comets is the same water that's in the sea. Not similar, the same. Because water carries a signature, a kind of chemical fingerprint that tells you where it was made and doesn't lie. And in the 1980s and 90s, we finally got close enough to comets to read theirs. The fingerprint did not match. When we measured the ice coming off comet after comet, the signature came back wrong. Consistently, stubbornly wrong. Different from the water in Earth's oceans by roughly a factor of 2. Whatever filled the sea, most of the comets we checked could not have been the main source. The suspect that everyone had trusted for decades, the obvious culprit sitting right there in the sky, was ruled out by its own water. And that raises the question that decides everything. What exactly is this fingerprint? This single ratio that can walk into the room and clear an entire population of icy worlds of a crime the whole field was sure they'd committed. Because the same test that eliminated the comets is about to be turned on a very different suspect. One whose water was never frozen on the outside at all, but locked deep inside the rock. Start with the atoms, because this whole story turns on a single one. Water is 2 hydrogen and 1 oxygen. That's what everyone learns. But not all hydrogen is the same. Almost all of it is the plain kind, a single proton, nothing else. A tiny fraction of hydrogen atoms carry an extra piece in the nucleus, a neutron, which doubles their weight. This heavier version is called deuterium. It behaves like ordinary hydrogen chemically. It bonds the same way, it makes water the same way. But it is twice as heavy, and that difference is the whole game. Here's what that weight actually does, down where you can't see it. Picture 2 versions of the same water molecule sitting in the same puff of vapor, both getting jostled by heat. The lighter one is quicker off the mark. It escapes, it evaporates, it drifts away sooner. The heavy one, dragging that extra neutron, lags behind and tends to stay put, to condense, to lock into ice first. So every time water freezes or boils or gets blown around by starlight, the light and the heavy kind sort themselves a little differently. Do that near a hot young sun, and you strip out the heavy hydrogen at one rate. Do it in the frozen dark, far out past the planets, and you strip it at another. The temperature writes itself into the mix. So in any batch of water, some of the molecules are made with normal hydrogen, and some are made with the heavy kind. The ratio between them, how much heavy hydrogen there is compared to the light, is the fingerprint. Chemists write it as the deuterium to hydrogen ratio. You don't need the notation, you need the idea. It's a number. Every source of water in the solar system has one, and it's set by where and how that water formed. Here's why it can't be faked. That ratio gets locked in when the water first assembles, and it depends on temperature and distance from the sun. Cold water, made far out in the frozen dark, tends to carry more of the heavy hydrogen. Water made warmer, closer in, carries less. Once it's set, it travels. A rock can drift for billions of years, get flung across the solar system, smashed, buried, melted, and refrozen, and the ratio stays put. It rides inside the water like a serial number stamped into the metal. Melt the object down, and you still read the same number. That's why it convicts and clears. You can't argue with it, and the object can't lie about where it was born. So when the comet ice came back with a ratio roughly double the ocean's, that wasn't a matter of opinion. The comets were made in colder country than the sea was. Different birthplace. Case closed on most of them. Now turn the same test on a very different suspect. Out past Mars, in the asteroid belt and beyond, there's a class of dark, sooty objects called carbonaceous asteroids. They're some of the oldest, least changed material in the whole solar system. Leftover crumbs from before the planets finished forming. What makes them interesting is the way they carry water. Not the way a comet does. A comet wears its water as ice, frozen on and through it, glazed onto the outside, ready to boil off the moment it nears the sun. A carbonaceous asteroid doesn't wear its water. It has it built in. The water is chemically bound into the minerals. Hydrogen and oxygen woven into the crystal structure of the rock, held there not by cold, but by chemistry. This is the difference between a snowball and a wet sponge that has dried into stone. The snowball loses everything when it warms. The stone holds on. Get down to the scale of a single crystal, and you can almost see it. The water isn't sitting in pockets. Individual hydrogen atoms are latched onto the mineral lattice, part of the architecture, spaced through the rock, atom by atom. You could heat one of these asteroids well past the point where any ice would have vaporized, and the bound water would still be there, gripped inside the mineral. That's what lets it survive the journey sunward, across the warm zone, all the way to a dry planet. Ice would never make it. Rock-bound water can. So we have two candidates and one test. Bring them together. Take the fingerprint of Earth's oceans. Take the fingerprint of the carbonaceous asteroids, measured both in the meteorites that fell from them and, later, from samples brought straight back from asteroids in space. Lay the two numbers side by side. They fit. Not roughly, closely. The heavy-to-light hydrogen ratio in these asteroids sits right on top of the oceans, near enough to be the same water. Where the comets missed by a factor of 2, the asteroids land almost dead on. The suspect nobody had wanted to look at. The dark, dull, unglamorous rocks that don't even grow a tail turned out to carry water that matches the sea. Almost. There's a leftover. The match is close enough to make asteroids the leading source, but not so perfect that it's the only source. There's a small discrepancy still sitting there, unexplained, which means the sea might be a blend, mostly asteroid water, with something else stirred in. Hold on to that gap. It doesn't go away. But matching the water isn't enough. You have to get it here. And that means the sky had to physically throw wet rock at the young Earth in enormous quantities, and you need a force big enough to do it. Here's the machinery. The carbonaceous asteroids formed out past Mars, well beyond Earth's orbit, in colder country where their water could get built into the rock. To fill the oceans, that material had to be moved, hurled inward across tens of millions of miles, onto paths that crossed Earth. What moves that much rock? The giant planets. In the early solar system, Jupiter and Saturn hadn't settled into the orbits they hold now. As they interacted with the disk of leftover debris and with each other, their orbits shifted. And when a planet that size moves, its gravity reaches out and stirs everything around it. The models that best fit the evidence have the giants migrating, Jupiter and Saturn falling into a resonance, where one orbits in a clean ratio to the other, and their combined pull hammering the small bodies of the outer belt. That resonance acts like a lever. It destabilizes the orbits of the icy and wet asteroids, and flings a wave of them inward, across the inner solar system, into the terrestrial planets. A violent, system-wide sweep, delivering water-bearing rock to a dry Earth in a relatively short span. That's what the mechanism requires. Not a gentle drizzle of comets over billions of years, but a giant reorganization of the solar system. The biggest planets shifting their orbits and, in doing so, raking a spray of wet asteroids down onto the inner worlds. The water gets here because the architecture of the whole system rearranged itself and threw it at us. So now we have a source that matches and the delivery truck big enough to do the job. It should be settled. It isn't. Because there's a collision in the way that ruins the neat timeline. Early in Earth's life, something the size of a small planet slammed into it. A body often called Theia, roughly Mars-sized, struck a glancing, catastrophic blow. The energy was almost incomprehensible. Enough to melt and partly vaporize the outer Earth, enough to blast a colossal amount of debris into orbit. That debris gathered into the moon. This is the leading explanation for why the moon exists, and the evidence in the rocks backs it hard. Now think about what that impact does to water. It turns the surface of the planet into a magma ocean, glowing thousands of degrees. Any water on or near the surface at that moment doesn't survive. It vaporizes, and a good deal of it escapes to space. An impact violent enough to build a moon is violent enough to strip the young Earth of much of whatever water it had. So this splits the whole story in two. Either the water we have arrived after the moon-forming impact, delivered by that inward wave of wet asteroids once the fireworks were over, refilling a planet that had just been scorched dry. Or the water somehow survived, tucked deep inside, far enough down that even a moon-making blow couldn't reach it all. A fork, not a solution. Two roads, and the evidence hasn't fully picked one. And then the ground shifts under the whole question. Because when you look at the oldest meteorites we have, chunks of material that formed before Earth was even finished, the original crumbs of the solar system, they carry water too. And the crucial part, that water didn't get added later. It formed together with the rock, at the same time, in the same place, bound into the minerals as they first crystallized. The building blocks themselves were already wet. A little damp, at least. Not the bone-dry pellets the frostline argument assumed. Read what that does to everything above. The whole mystery started from the premise that Earth formed dry, in a zone that couldn't hold water, so the water had to be imported. But if the very grains that assembled into Earth already had water locked inside them, water that came with the rock, not on top of it, then the planet may have been born, at least partly, wet. Included from the start, not delivered from outside. The oceans, or the seed of them, could have been in the mix from the first day, riding inside the rock the same way that deep mantle water rides inside ringwoodite now. So which is it? Was the water baked into Earth from the start, carried in the minerals of its own building blocks? Was it thrown here afterward, in a spray of wet asteroids flung inward by shifting giant planets, refilling a world scorched dry by the impact that made the moon? Or, and this is the possibility the fingerprints keep pointing at, with that stubborn leftover gap that won't close, was it both? A planet born damp and then topped up from the sky, the sea a blend of two waters with two different histories that happen to read almost the same. Every one of those stories fits some of the evidence, and none of them fits all of it. The water is here. 2/3 of the surface, and maybe several oceans more sealed in the rock below. And we still cannot say, with the confidence you'd expect for something this basic, how it came to be under our feet at all. Two stories, both good, and they refuse to become one story. That's where we're stuck. On one side, Earth-born wet, the water riding inside its own building blocks from the first day. On the other, Earth scorched dry by the collision that made the moon, then refilled from the sky by wet asteroids flung inward. And the reason these two pictures won't merge is that they need the same water to do two contradictory things. Born wet water has to survive an impact that vaporized the surface of the planet. Delivered water has to arrive in exactly the right amount, with exactly the right fingerprint, to look identical to whatever was already here. Push on either story, and it fits most of the evidence and cracks somewhere. Neither one wins clean. And there's a third source hardly anyone brings up. Consider the solar wind. The sun doesn't just shine, it blows. A constant stream of particles pouring outward, most of them bare hydrogen nuclei, single protons moving fast. Now take a grain of dust in the early disk, floating with no atmosphere to shield it. Those protons slam into the grain and lodge in its surface. Down at the level of individual atoms, a hydrogen nucleus buried in a mineral can grab an oxygen already in the rock and become, quite literally, a molecule of water. Not delivered as ice, not baked in during formation, manufactured on the spot, one atom at a time, on the skin of dust grains by the wind off the sun. Samples of asteroid dust brought back to Earth show exactly this: water made right there in the outer few molecular layers of the grains. It's a whole recipe for wet rock that the frost line argument never accounted for. And it points, faintly, at that leftover gap in the fingerprint. A little of the sea might not have come from anywhere. It might have been assembled in place. But the hardest piece to explain is still the one under our feet. The water in the deep mantle. It's the hardest because we can barely touch it. You can measure comet ice with a spacecraft flyby. You can measure asteroid water in a meteorite that lands in a field. But the transition zone starts 400 miles down, and nothing we build goes anywhere near it. The deepest hole ever drilled reached about 7.5 miles before the rock got too hot and too soft to go on. 7.5 miles into a planet whose water reservoir sits 400 miles down. We are scratching the varnish and trying to describe the wood. Which is why one flaw in one diamond changed the whole argument. A diamond forms deep and gets carried up fast by violent eruptions, and sometimes, as it crystallizes, it seals a speck of its surroundings inside itself. A mineral inclusion, locked and protected. A sample of the depths that can't leak or react on the way up. In 2014, a diamond from Brazil turned out to have a grain of ringwoodite trapped inside. And that ringwoodite was more than 1 part in 100 water by weight. Solid rock, and water woven right through the crystal. That single flaw was the first direct, physical proof that the transition zone actually holds the water the lab experiments predicted. One accidental sample, delivered by the planet itself, and the argument shifted from maybe to yes, it's really down there. Now let that number breathe for a second, because it opens a crack in something you thought was fixed. If the mantle can hold that much water, then the ocean and the interior aren't separate. They trade. Slabs of wet seafloor slide down into the mantle at the trenches, carrying water into the rock. Deep water comes back up through volcanoes. The sea, in other words, is leaking downward and being topped up from below all the time. Sea level isn't a line the water settles at. It's a balance, a slow negotiation, between the ocean on top and the far larger reservoir beneath. And the surface is just where the two happen to meet right now. If the deep Earth decided to drink a little more, the ocean would fall. It has probably been higher and lower across the planet's life for exactly this reason. And once you understand that Earth's water is this tangled, borne in, thrown in, wind-made, and constantly swapped between rock and sea, you can turn the same puzzle on other worlds, and it gets worse. There are planets forming in the dry zones of other stars that, by every rule we thought we knew, should be bone dry. And out here in our own system, past the frost line, there are moons, Europa, Enceladus, small, icy bodies that have no business holding oceans. And they hold oceans anyway. Liquid water sloshing under crusts of ice, kept warm by the flexing pull of the giant planets they circle. The rule was simple. Water lives out there, not in here. Every world we look at closely breaks the rule in one direction or the other. The dry places have water. The frozen places have oceans. The tidy map has no honest borders left. So come back to where we started. More water than every ocean, perhaps, locked in a mineral 400 miles down. Water that has never seen the sky. When I opened with that, it sounded like a curiosity. Now it sounds like the center of the whole thing. Because the question was never really where the oceans came from. It was how a planet in the driest corner of the young solar system ended up soaked to the core, and the answer seems to be that it didn't come from any single place. It was born with some, given more, and it has been quietly hiding the majority of it in the rock the entire time. If any of this made the ground under you feel a little less solid, subscribe, leave a like, and stay a while. There's more strangeness where this came from. Here's what I keep circling back to. The water we can see, the seas and the rain, is the thin skin. The real reservoir is the one we can't reach, can't drill to, can barely sample except when a diamond happens to bring us a grain of it by accident. We've read the fingerprints of comets and asteroids across the whole solar system, and we still can't say for certain how our own ocean got here. And there's a question hiding underneath that one. If the mantle holds several oceans worth, and it trades water with the surface over the planet's lifetime, what happens when the trade tips? The deep Earth has been keeping most of our water out of sight for 4.5 billion years. We've been assuming it will keep giving it back. But that's an assumption, not a measurement. And nobody yet knows which way the balance is drifting.